Standing upright feels effortless. Most of us never think about balance until the day we suddenly lose it. Maybe you stumble on a curb, miss a step, or notice you feel less steady than you used to. It often seems like balance simply disappears with age. But scientists discovered something much more interesting. Balance isn't a single ability that gradually wears out. It is the result of several body systems working together every second you are standing, walking, turning, or reaching for something. That raises an important question. If balance depends on so many different systems, which ones are responsible for keeping us upright? Researchers wanted to answer that question too. By studying people of different ages, measuring movement, and observing what happened after injuries and neurological disorders, they discovered that balance is far more complex than anyone once believed. Understanding why we lose balance doesn't begin with muscles. It begins by understanding how the body constantly knows where you are, how you're moving, and when you're about to fall. That discovery completely changed the way scientists think about balance. As scientists began studying balance, they noticed something that didn't fit the usual explanation. If aging alone caused balance to decline, then everyone should lose balance at roughly the same rate. But that isn't what researchers observed. Some people remained remarkably steady well into their 80s and 90s. Others began having difficulty much earlier, even when they were similar in age. Researchers also found that balance could change after injuries, certain diseases, vision problems, inner ear disorders, or long periods of inactivity. That suggested something important. Age was influencing balance, but it wasn't acting alone. Scientists realized they weren't looking at one system gradually wearing out. They were looking at several different systems interacting with one another. If one system became less accurate, the others often had to compensate. That discovery completely changed the investigation. The question was no longer, why do we lose balance with age? The new question became, what systems must work together every second to keep a person standing upright without falling? Once scientists realized that aging alone couldn't explain balance, they needed a new approach. How do you study something that happens every second without us even noticing? Researchers designed experiments that challenged balance in controlled ways. They asked people to stand still, with their eyes open and then closed. They observed how people walked across different surfaces, recovered from small pushes, turned quickly, and responded when the ground became unstable. They also studied individuals with specific medical conditions. Some had vision problems. Others had disorders affecting the inner ear. Some had nerve damage that reduced sensation in their feet, while others had muscle weakness or neurological diseases. Each condition affected balance differently. That was the clue. If one problem changed balance in one way and another problem changed it in another way, then balance couldn't depend on a single system. The evidence pointed to something much more complex. Scientists were beginning to uncover a network of systems working together continuously to keep us upright. But which system was providing the brain with the information it needed first? As the evidence continued to grow, scientists reached a conclusion they hadn't expected. They weren't looking for several balance systems. They were looking for one. Instead, the research revealed something much more interesting. There is no single organ, muscle, or part of the brain responsible for balance by itself. Balance is an ongoing collaboration. Every second you are standing, walking, turning your head, or reaching for an object, the brain is receiving information from several different body systems at the same time. It compares those signals, decides whether they agree, and sends out rapid corrections, often before you are even aware that anything has changed. This completely changed the scientific understanding of balance. The question was no longer, where is the balance system? The real question became, which body systems are constantly sending information to the brain, and what happens when one of them becomes less accurate? To answer that, scientists began studying each system separately. The first one may surprise you because most people use it every second without ever realizing how important it is. Most people think their eyes are only for seeing. Scientists discovered they are also one of the brain's most important sources of balance information. Every second you are standing, your eyes are measuring where you are in relation to the environment around you. They detect movement, judge distances, identify the horizon, and provide constant updates about whether your body is remaining stable or beginning to sway. Researchers demonstrated just how important vision is with a simple experiment. Ask someone to stand on one leg with their eyes open. Most people can maintain their balance for a reasonable amount of time. Now ask them to close their eyes. For many people, the task immediately becomes much more difficult. Nothing about their muscles changed. Nothing about their strength changed. The only thing that changed was the amount of information reaching the brain. Scientists realized vision provides one of the major streams of information the brain uses to keep us upright. But the experiment revealed something else. Even with your eyes closed, many people can still remain standing. If vision isn't the whole answer, what other system is still telling the brain where your body is in space? Scientists eventually realized there wasn't a single reason balance changes as we age. Some biological changes do occur over time. Vision may become less precise, some vestibular sensory cells are gradually lost, muscle power often declines, and nerve signals can become slightly slower. When scientists temporarily removed visual information, they discovered people could still maintain some balance. That meant another system was continuing to provide the brain with critical information. The answer was hidden inside the inner ear. It is called the vestibular system. Although most people have never heard of it, this small sensory system constantly monitors the position and movement of your head. Tiny fluid-filled canals and specialized sensory organs detect when you turn, tilt, speed up, slow down, or change direction. Every movement creates signals that travel to the brain within fractions of a second. Researchers quickly realized why this system is so important. Imagine turning your head while walking. Your eyes alone cannot tell the brain how your head is accelerating or rotating quickly enough to maintain stability. The vestibular system fills in that missing information, allowing the brain to coordinate your eyes, posture, and muscles so the world doesn't appear to spin every time you move. People with vestibular disorders often describe dizziness, unsteadiness, or feeling as though the room is moving around them. Their muscles may still be strong, yet balance becomes much more difficult because one of the brain's major information sources has become unreliable. But even the vestibular system isn't enough by itself. How does the brain know exactly where your arms, legs, and feet are without having to look at them? Scientists had now identified two major sources of balance information: vision and the vestibular system. But one important question remained. How does the brain know where your arms, legs, and feet are without having to look at them? The answer is a remarkable system called proprioception. Throughout your muscles, tendons, joints, and even your skin are specialized sensory receptors that constantly send information to the brain. They report the position of your limbs, how much your muscles are stretching, how much force they are producing, and whether your body is shifting forward, backward, or sideways. This information is updated continuously, often without you ever becoming aware of it. That is why you can button a shirt without watching your hands, climb stairs in dim light, or touch your finger to your nose with your eyes closed. Scientists realized proprioception provides the brain with an internal map of the body. Without that map, movement becomes slower, less precise, and balance becomes much more difficult because the brain no longer knows exactly where the body is in space. But receiving information is only part of the story. Someone still has to compare all of these signals, decide which ones are reliable, and send instructions to the muscles before you fall. By now, scientists understood that vision, the vestibular system, and proprioception each provide different pieces of information. But collecting information isn't enough. Someone has to combine it all. That job belongs to the brain. Every second, the brain receives millions of signals from the eyes, the inner ear, muscles, tendons, joints, and skin. It rapidly compares those signals, decides whether they agree, and sends instructions to the muscles that keep you upright. Remarkably, this entire process happens in fractions of a second, long before you consciously realize you've started to lose balance. Scientists discovered that maintaining balance isn't about one system working perfectly. It's about several systems communicating accurately and continuously. When the information agrees, movement feels smooth and effortless. But if vision becomes less reliable, the vestibular system changes, proprioception becomes less accurate, nerve conduction slows, or muscles respond more slowly, the brain has a much harder job. It must make decisions using information that is less precise or arrives too late. That is why balance can become less stable even when no single system has completely failed. So what changes as we age that makes this remarkable teamwork gradually become less efficient? Scientists eventually realized there wasn't a single reason balance changes as we age. Some biological changes do occur over time. Vision may become less precise. Some vestibular sensory cells are gradually lost. Muscle power often declines, and nerve signals can become slightly slower. But researchers discovered that time is only part of the story. These systems are also highly adaptive. The brain continually updates its movement programs based on the challenges it receives. Muscles remain stronger when they are regularly asked to produce force. Proprioception improves when we continue exposing the body to varied movements, uneven surfaces, and balance challenges. Even the nervous system becomes more efficient when it is repeatedly required to coordinate complex movements. When those challenges disappear, adaptation slows. The body begins investing fewer resources in abilities it is no longer being asked to maintain. That is why two people of the same age can have very different balance. One body continues receiving the signal that balance still matters. The other gradually receives fewer of those signals. Scientists didn't discover that balance is controlled by age alone. They discovered that balance is an adaptive system, and adaptive systems remain stronger when they continue adapting. Adaptation is survival. So what changes as we age that makes this remarkable teamwork gradually become less efficient?